Okay, so this is the third video. In the first one, we talked about Lewis dot symbols and covalent bonds. In the last one, we kind of introduced the idea of electronegativity. Now we're going to piece this all together and build Lewis structures in a very nice systematic way. So instead of just drawing the dots and hoping they connect right, we're going to come up with a more systematic approach. Okay, so there is a step-by-step process. We'll figure it out. We'll just kind of do it one step at a time, and I'm actually going to work through two examples while we do this. Okay. So the first step is to determine the total number of valence electrons in the molecule. So determine total number of valence electrons in the molecule. And these valence electrons are all the dots, and they're going to have to be used somewhere, either as lone pairs or as bonds, somewhere in the process. Okay, so we're gonna just kind of work through two examples. One is NF3, another is COCl2. Okay, NF3 is a completely random, pointless molecule. COCl2 is phosgene. It's actually like a nerve gas they used in like World War II to like kill people. Kind of horrifying stuff, but it makes for a really good Lewis structure example. Okay, so what we do is nitrogen is in column 5. It has 5 valence electrons. Fluorine is in column 7, so 7, and there's 3 of those, so 7 times 3. 21 plus 5 should be 26 electrons. You will almost always get a even number here. If you don't, double check your math. It is possible to have an odd number, but for right now, we don't even know how to deal with that. We will by the end of the chapter, but even after I teach you how to deal with it, even is still the most likely option. Okay. Carbon, column 4, should have 4 valence electrons. Oxygen, column 6. Chlorine is in column 7. We should have 2 of those. So 10 plus 14, we should have 24 electrons. You'll notice that they're both even. Okay, so what this means is we have 26 electrons that we have to use in the form of nitrogens, or sorry, in the form of single bonds, double bonds, triple bonds, or those dots for lone pairs. Over here on this one, we have 24 electrons that we have to use in the form of single bonds, double bonds, or lone pairs or whatever, okay? Step 2 is actually kind of the most difficult step. That's okay. Basically what you do is you connect the atoms together. There's some guidance for this. The least electronegative atom is the most likely to be the central atom, to be in the middle and everything else is sticking off of it. So the least electronegative atom is usually the central atom. I'm just going to put is the central atom. There are some exceptions to that, but not very often. And what we're going to see throughout this entire chapter is anytime we have a rule, hydrogen is the exception. Hydrogen cannot be the central atom. It can only have one bond ever, so it can't be the central atom, okay? Also, for what it's worth, if you have an acid of any kind, hydrogens are, I'm going to put usually attached to oxygen in acids. Neither of these are acids and neither of them even have hydrogens, but sometimes if you have an acid, the hydrogen is not usually attached to the central atom, it's sticking off of an oxygen. So it's possible to have more than one central atom, and that's okay. So let's just try this for these examples. So between nitrogen and fluorine, the general trend is fluorine is the most electronegative atom on the periodic table. The farther away from fluorine it is, the more likely it is to be the central atom. So between nitrogen and fluorine, which is the most electronegative atom on the periodic table, nitrogen's less electronegative. So for our examples here, nitrogen's going to go in the center, and the 3 fluorines are going to be attached to it. However you want to angle them off of there is great. Most people do 90-degree angles, but I don't care, really. In the real world, they don't even form 90-degree angles anyway, so I don't care. Okay, on this one, our choices are carbon, oxygen, and chlorine. Oxygen and chlorine are right next to fluorine, but carbon's pretty far away. Carbon loves being a central atom. It's the reason organic chemistry is a thing. So I'm going to try to make these look kind of similar. So the oxygen and the 2 chlorines are going to be attached. Doesn't really matter where you put them. I typically make mine symmetrical, but you don't have to. It's really not a big deal. So we need to do some bookkeeping. We have been using electrons out of this total. Each line counts as 2 electrons, and we have 26 total, so we've used 2, 4, 6. We have 6 electrons used, so we should have 20 electrons left to put somewhere. Same thing on this one. We've used 6 electrons, but we only had 24 to start with, so this time we only have 18 electrons left. Okay, not too bad. All right, step 3. What you're going to do is you're going to place lone pairs on the non-central atoms, the terminal atoms, until they have a full octet. And, as per usual, hydrogen is the exception. Hydrogen will never, ever, ever get dots. Please don't ever put dots on hydrogen. So, place lone pairs, which are the pairs of electrons not part of a bond, on terminal atoms, so in other words, not the central atom, to form octets. Hydrogen never gets lone pairs. Okay? So, you wouldn't typically redraw this for every step, but I'm redrawing it so you can see each rule applied one at a time here. Okay, so this fluorine would like to have 8. Right now it has access to 2, so 4, 6, 8. 4, 6, 8. 4, 6, 8. On this one, chlorine and oxygen, same idea. Okay, so now the non-central atoms, so the nitrogen was the central atom, the 3 fluorines have been taken care of. They should have octets at this point. Okay, let's do some bookkeeping. We've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So 24 electrons used. We should have 2 electrons left. Same setup over here. We've used 24 electrons. There are 0 electrons left, which will affect the next step, but that's okay. Okay. So step 4 for this is to basically place any remaining lone pairs on the central atom. I don't know why this isn't focusing, but we'll figure it out. Okay. Place any remaining electrons as lone pairs on the central atom. Okay. So, for the NF3, we had 2 electrons left. I'm going to redraw this. We had the fluorines that all had their 3 lone pairs and their single bond. Okay. We had 2 electrons left. I put them on the nitrogen. The other compound, there were no electrons, so I'm not even going to do this step. Okay. Step 5. What you're going to do is check for octets. Okay, and what you're going to do is, if there is anything that does not have an octet, so if you check for octets and everything has an octet, you're probably good. There's still one more step after this. Okay. If no, what you're going to do is you're going to steal, like you would steal electrons from the terminal atoms and force them to become shared pairs to form double bonds or triple bonds. So use lone pairs of terminal atoms to form double or triple bonds. Okay, so for NF3, redrawing it, we're going to need to evaluate to see if everything has an octet. And for COCl2, we need to do the same thing. Okay, so just need something to point with. So this fluorine has 2, 4, 6, 8. This fluorine has 2, 4, 6, 8. This fluorine has 2, 4, 6, 8. And this nitrogen has 2, 4, 6, 8. Remember, the bonds count towards both atoms connected to it. So everything as an octet, we're probably good. We still have one more step to double check everything, but that's okay. For this one, this has 2, 4, 6, 8. This has 2, 4, 6, 8. This has 2, 4, 6, 8. But the carbon only has 2, 4, 6. So we are going to need to steal some electrons from somebody. We have two choices, actually. One option is to steal electrons from one of the chlorines. There are two equivalent choices, so I don't really care which one you pick. Or we could steal from an oxygen. We're going to get two different answers depending on which one we pick, and one answer is probably better than the other. So if we choose one of the chlorines, what we would do is we would take one of these three pairs of lone pairs of electrons, bring it down, and form another bond, and get a double bond here. But now we would only have 2 lone pairs instead of 3. And on the other side, everything else is still the same. But if you check, this has 2, 4, 6, 8. This carbon now has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. Chlorine, 2, 4, 6, 8. Great. If we had chosen the oxygen instead, we would get this stuff all left the same, and we'd have a double bond to the oxygen. Okay. And we get 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8. Everything's got 8. One of these is better than the other, and we need to figure out which one. Okay, so which is right? Or are they both right? Or how do we know? Okay, so this is where step 6 kicks in. Step 6 is tedious, but really not that difficult. It's the first bit of math we're going to see for a little while, but it's subtraction of whole numbers. Step 6 is to check the formal charges. So there is a formula for how to check formal charges, and every textbook makes it sound like the most complicated thing ever. I'm just going to read you how to do formal charges, and I'm going to write out how I do it. To calculate formal charges, you're going to need to do this for every individual atom in your molecule. And what you do is you take the number of valence electrons that you started with. So like for carbon, you would use 4, oxygen, you would use 6, so on. Minus the number of electrons in lone pairs minus 1/2 the number of electrons in bonded pairs. That sounds tedious. What I always tell people to do, to calculate formal charge of an atom, it's number of valence electrons, can't get around that one. So however many valence electrons it's supposed to have to start with, valence electrons, minus dots, minus lines, and we only care about what's attached to that atom. So I'm going to rewrite those molecules and we're going to check the formal charges. But this will allow us to decide which is the better molecule. So in general, if you have more than one choice, like we did on that COCl2, usually, there are some exceptions to this, usually the structure with the lowest, with the smallest charges, let's go with that, smallest charges is the best. Okay, so if you have choices to make, this will help you decide that. Your overall formal charges should add up to the overall charge of the molecule. So these ones all should add up to 0 even if you get charges, okay? Just because it adds up to the total charge doesn't mean that it's the right answer. It just means that you didn't screw up counting up the formal charges, okay? So let's look at those two examples. So NF3, we really had no choices on this, but let's see what we get. I'm going to do formal charges in, I guess, red. Why not? Okay, just a different color to be able to see it easily. We have to do every atom. So for fluorine, this was element 7, or in column 7A, so it has 7 valence electrons, minus dots, minus lines. Fluorine has 2, 4, 6, and 1 bond would be 0. This fluorine is in exactly the same situation, so it's also 0, and so is this one. Okay, so those are all zeros, so that's good. We want smaller charges. 0 is as small as you can get. For nitrogen, that has 5 valence electrons minus 2 dots minus 3 lines is 0. So since everything is 0, this is probably the best answer we could come up with. This is the Lewis structure for NF3. Okay. On the other problem, we had 2 possible choices. I'm going to redraw them just so we can check them each separately. We had a double bonded chlorine as one option, and we had another option where it was a double bonded oxygen. Both of these had octets. They both look like they should be perfectly happy, great molecules. The octet rule was satisfied. This will help us decide which of these is a better molecule. So if we check up here, this chlorine is in column 7A. So it's got 7 valence electrons, minus 6 dots, minus 1 line is 0. This oxygen has 6 valence electrons. It's in column 6A. Sorry, 6A. Minus 6 dots, minus 1 line is -1. Okay. Carbon has 4 minus 0 dots minus 4 lines is 0. That's encouraging. And this chlorine is 7 minus 1, 2, 3, 4. Accidentally wrote on the page, sorry. Minus 2 is +1. So we have a +1 and a -1, so it does add up to 0, but we do have some charges. If we compare that to this molecule, this chlorine is 7 minus 6 minus 1 is 0. This chlorine is 7 minus 6 minus 1 is 0. This carbon is 4 minus 0 minus 4 is 0. And this oxygen is 6 minus 4 minus 2 is 0. Since everything is 0, this is the better molecule. That one is not stable compared to this. So your formal charges can help you, like if you have choices to make of like where to put double bonds, where to put triple bonds, the formal charges are going to dictate what is the most stable structure. I expect you to check the formal charges of every Lewis structure you ever draw. It is critically important to the process, okay? So I will also point out that in this process, we didn't make any double bonds until step 5. One of the most common mistakes that people make when they're doing Lewis structures is they're like, oh, I think there needs to be a double bond here. And they'll do that like the first step when you're like connecting step 2, when you're like connecting all the atoms. They'll be like, I don't know, maybe there's a double bond there. They'll just randomly guess about double bonds. You have to do the process in this order for it to work every time. It is entirely possible to guess correctly, and it's also possible to just draw the dots and hope to connect things right. This gets really complicated if you have things that are charges or things that ignore the octet rule, which is going to be an entire third of this chapter. We're going to have to deal with that, and this process works every time. It is tedious, but it works. All right, thank you. I don't know. Good luck.